This video is on Russell's paradox. So this is a paradox concerning the nature of sets from Bertrand Russell in the early 1900s. It's sort of just an interesting thing to think about, not necessarily something that will especially apply to homework or quizzes or anything else in this class, but just kind of a fun, short topic. So consider the following set of sets. The set A is defined to be sets X such that X is a set and X is not an element of itself. So in other words, A is the set of sets that do not contain themselves as elements. So that's a strange definition. Let's think about this a little bit. First of all, let's observe that most sets are in A. So for example, let's just say that the set C is equal to the number 1 and the number 2. So if that's the set C, then yes, C is a set, and C does not contain itself as an element. C is not itself an element of C, right? Because, 1 is an element of C, 2 is an element of C, 1 is an element of C, 2 is an element of C, but the entire set, 1, 2, is not an element of C. It is true that it is a subset of C because every set has itself as a subset, but it's not an element of itself. So that means because the set C is not an element of itself, that means that C is an element of A, the set of sets that do not contain themselves as elements. Okay, so could anything be in A? Well, here's another thing that we're going to define, and this is a weird one. So we're going to define B to be the set of just infinitely many nested braces. So these are just, there's no, the element of, so the element of this set is this set, and the element of the next one is this set, and so on. So B is a set of infinitely many nested braces. Then, so infinitely many, that part's important. So then B actually is an element of itself, because if we think about infinity minus 1, that's still infinity. And so that means that, yes, it is the case that this is equal to B, and this larger nested set is also equal to B. Each of those is a set with infinitely many nested braces. So B is an element of itself. This is B, and it is an element of itself, the set B. So because B has the property that B is an element of itself as a set, that means that it does not meet this quality, this criteria for being in the set A, and therefore that means that B is not an element of the set A. So we see examples of things that are in the set A and things that are not in the set A. So here is the big question. Is this set A an element of itself, or is it not an element of itself? This is a collection of things that are sets that have this property or do not have this property. So it should be the case that any set either has the property or does not have the property. It seems as though it must be the case that either A must be in A or A must be an A complement. So what I'd like you to do now is think for a moment. In either of these cases, what is the logical conclusion? So assume that A is an element of A. What does that mean when you think back to the definition of being an element of A? And assume that A is not an element of A. Again, what does that mean in terms of not being an element of this set? So think about each of these. Do give it a good moment, and we'll talk about it in a second. Okay, so again, A is the collection of sets X such that X is a set and X is not an element of itself. A is the set of sets that do not contain themselves as elements. So if A is in A, then by definition, A does not contain itself as an element. That's the definition of being an A. So if A is in that set, that means that by definition, A is not an element of A by definition. But what do we see? We see a contradiction here, right? So if A is an element of A, then A is not an element of A. These are opposite things that cannot be true at the same time. And so this is a contradiction. We sometimes draw that as two sort of angry arrows pointing at each other. This is a contradiction. And on the other hand, if we make the assumption then that A is not an element of A, what does that mean? If A is not an element of A, then A is a set and A is not an element of A. Well, this is the definition of being in A. So if we look back here, the definition of being in A, in the set A, is that the set, is a set, and the set does not contain itself. Those criteria are met, and so this implies that A is an element of A. So again, we have the same contradiction. We see that A is not an element of A, implies that A must be an element of A, and again, this is a contradiction. And that contradiction is Russell's paradox. You can, if you want to think about this contradiction or this paradox in a different way, or if you want to, tell your less mathematical friends about this paradox, here's another way to phrase it. The barber of Seville cuts the hair of everyone in town that does not cut their own hair, and no one else. So if someone cuts their own hair, he does not cut their hair. If they do not cut their own hair, then he does. I'm sure that a lot of salons have this policy, like, okay, if you're going to chop away your hair and do weird things to it, I'm not touching it. Maybe some fancier salons have that policy. Anyway, so assuming that this is true, then does the barber cut his own hair? So we arrive at the same paradox. If he does cut his own hair, then, well, he will not cut the hair of anyone who cuts their own hair. So if he does cut his own hair, this implies that he doesn't. And if he does not cut his own hair, then by definition, he cuts the hair of everyone in town that cuts their own hair. So if he does not cut his own hair, it implies that he does cut his own hair. So again, we arrive at the same paradox, just sort of phrased in a different way. So this paradox about sets, or things that kind of, at least, potentially one could call a set, led some mathematicians to examine more carefully what can and cannot be a set. And the mathematical community settled on a collection of axioms, or in other words, statements assumed to be true for set theory. And these are called the Zermelo-Fraenkel axioms. So these are, pretty abstract and specific and don't really affect daily mathematical life, even for people with PhDs in most area of mathematics. Like in general, for these axioms to matter, you'd have to purposely construct these sort of weird situations, such as Russell's paradox above. So, there are people who get their PhDs or that do research specifically in set theory, and that's sort of a weird, very abstract level area of mathematics. We're thinking about these deeper, weird things about sets. But in general, for most areas of mathematics, these axioms aren't really going to come up, again, unless you purposely try to get there. So these axioms do make this theory consistent and avoids strange paradoxes like those above. Essentially, one of those axioms prevents that weird set B, being the collection of nested intervals where there's infinitely many of them, from being called a set. So there are certain axioms, assumptions that are made about sets that prevent things like Russell's paradox from occurring.